All right, on to number 2 from the 2021 FRQ set. This problem, a little bit more challenging, but let's go ahead and take a crack at it and see how many points we can get. So it says a block of mass M starts from rest at point A and travels with negligible friction through the loop onto a horizontal surface where the block makes contact with a spring. K equals a weird thing. All motion of the spring is in the horizontal direction. Point C is the highest point of the loop, and B is the rightmost point of the loop. All answers in terms of the algebraic things. On a dot, which represents the block, draw an arrow to represent the direction of the acceleration of the block at point B in this picture. All right, so right off the bat, and they have a justification. This is where a lot of people would probably get this one wrong. I'm going to draw some stuff up here. At point B, there's a centripetal acceleration because it's going around in a circle. However, it's not going at a constant speed. So there is the acceleration of gravity acting on it. This is one of those two-dimensional accelerations. So the acceleration should be someplace around there. Arrow to represent it. The arrow must show start on the point. So yeah, it would be in that direction. So for the justification, you have to say there's A, C, and G, and we'll put that for now. I don't know what they're expecting for a full answer. But going back to this picture, they give us a height, no angle, so I'm guessing this is going to be a conservation of energy problem here. Then there's a loop, so going up through the loop and around, and then there's a spring. This just smells like a big conservation of energy problem at some point. Derive an expression for the speed v of the block at point B. So how fast is it going at point B? This is conservation of energy. So at point B, it's gone down a ramp. It's not all the way to the top, it's halfway up, right? So we got the initial point, and so we would have initial height. How do they label it? It's lowercase h. So we'd have UG initial is going to turn into UG final plus some kinetic energy final at point B. But we know that just putting that isn't enough, so let's go ahead and put m times g times h equals m times g times, if we're in the middle of the circle, we're 1 radius away from the bottom. So I'll put that as r plus 1/2 m times the v squared. And from there, we'd have to solve that. Number 2, derive an expression for the magnitude of the net force on the block at point B. So this is going to be based off of that idea, the magnitude of the net force. It's going to be a combination of the centripetal force and the gravitational force. And when you're dealing with 2D forces, you got to do the old Pythagorean theorem. So the net force would be equal to the square root of Fc plus mg, squareds, Pythagorean theorem. And we'd have to do that. Yeah, move on. Let's see here. In terms of r, derive an expression for the minimum heights, h min, necessary for the block to maintain contact with the track through point C. So we talked about this before. If you're going through a loop and you get to the highest point of the loop, you've got centripetal force acting down on you, and you've got the gravitational force acting down on you, and the normal force from the track would be acting on you. Sorry, the centripetal force is the net force at the highest point if you're, don't have anything trying to slow you down tangentially to the track. So the normal force and the gravitational force combine to give you centripetal, but if you're trying to just keep contact and you want to go the slowest you can, so you release it from the least height above the ground on the track, that means you want the normal force to go to 0. So the you're looking for a speed where the centripetal force is equal to the weight force. So we'd have m v squared over the radius, and that would have to be equal to m times g. So that would give you the minimum velocity. But then what height do we need to go to get to that minimum velocity? That's going to be conservation of energy. So there's some minimum initial height that would give you, when you get to the top of the loop, which would be 2r. Yeah, 2r. And then that would go plus the 1/2 mv min squared, like I don't know if it's called vmin or what, but we're calling it vmin. So we'd have to solve all that. That's a lot. Let's see here. Part D, 10 seconds. It's determined that it's this and this. What's the spring compression? We're not going to be able to solve that, but we can at least set up compression to spring. It's an ideal. It's not an Is it an ideal spring? Did they say it's an ideal spring? Spring with spring constant K is equal to that. So the spring constant is a constant. It just happens to be really weird. It doesn't actually. Does it say it's an ideal spring? I guess because that's constant, we're supposed to assume it's an ideal spring. If it's an ideal spring, I know we went over time here, but we can say that the original potential energy at the highest point would turn into spring energy final because it comes to a rest. So we could say that's m times g times the h, whatever h is we're looking at. Because here it says release from a point greater than that at the point C. That's kind of confusing to me. But we could say that's equal to 1/2 kx squared. And then that would have to be solved. Anyways, we didn't get to the rest of that in 5 minutes. That was a little tricky problem. Then it's asking, why does there a flat segment? We can talk about that. And then on to problem 3. Problem 3 is not fun. Anyways, let's go ahead and take a look at some scoring guidelines for this problem and see what we got. See if we got any points here. So part A, for a single acceleration vector showing down to the left, that'd be 1 point. Now this, again, I think this is kind of tricky, and I think a lot of people would just put centripetal acceleration, or they might put the gravity acceleration. And so I think a lot of people probably wouldn't get that point. For justification, that the block is changing direction, centripetal acceleration toward the center of the circle, and gravitational downward. So yeah, I don't know if that's the best description, but we'll put these as like clouds, as like, yeah, maybe we got them. BI, for correct, using conservation energy of the block at point B. So I think we get that point. They wrote it kind of weird there, but I'll put that as a +1 for correctly substituting into the above equation. So this, for correctly substituting into the above equation, that doesn't say you get a point for the answers. It just says for correctly substituting. So if we substituted, that would be the point. Sometimes I just don't get College Board. Like, what does that mean? It's like, do you get a point for the right answer or not? Anyways, B2, for correctly substituting the expression for B from that into an expression for centripetal force, you get 1 point. For correctly we didn't do that. For correctly substituting into an equation for vector addition, using the Pythagorean theorem, you get 1 point. So BI, I don't know if we technically get that point then. We wrote that we would do this, but it's just 1 point for correctly substituting in. So that's a lot of vagary right there. I'm gonna have to say that we didn't get any points for that, but maybe we could have finished this and gone back and substituted in and got the that point there. It seems like they're plotting for double jeopardy protection. And let's see here for this. Got to scooch the screen over here. Part C. For correctly using conservation of energy for the speed of the block at point C, that's 1 point. So 1 point. What? Like this whole thing is 1 point? Wait, hold on. So if you set this up and you solve for the velocity at point C, that's 1 point. So you have to do all of the steps to get this. For correctly using conservation energy, it seems like that might get a point because we used conservation of energy. We just didn't solve it to an expression. And for correctly applying Newton's second law at point C. So, I mean, it seems like that could be worth 2 points. I don't know, man. There were some times, this is like post-pandemic, so I think the College Board is like lost it at some point and they forgot how to do problems, and it's just, the scoring on this one's insane. So then there'd be a third point. I'm gonna put these as cloud points, like, yeah, maybe we get it, maybe we don't. Because it's like we set it up but we didn't do whatever it is that they're actually talking about there. Part D, let me guess. Is it some vague thing? For correctly using conservation of energy for the block compressing the spring, for correctly substituting the gravitational elastic potential energies into an equation for the constant energy. Yeah, I think we get those 2 points. I put this and I put that. I'm going to call that as a not cloud point. Those aren't dreams, baby. Those are real. And so then we didn't finish it from there. And then part E and 1 and 2 are some things that we didn't look at for describing what's going on. But anyways, let's see what our real and potential points are. So we got 2 real, and then we've got 2 potentials. So 2 versus 4. Then it's 4 versus, we got another 4 there. So we got 4 real points and 4 potentials. So yeah, that's not looking great. It's either somewhere between 4 and 8. And the average score for this was 6.2. What do you know? That's between 4 and 8. So yeah, I think, that was a tricky one. They threw us for a loop on that one. But otherwise, I think, going through and finishing these up, there's some points on the table that we could get if we spent the next 10 minutes working on it still. Okay, I'm going to stop this one and go on to number 3.